Okay, so I'm just going to do a quick go through this and talk a little bit about the shocks and the speed of the shock and things. And I'm going to go through this a little bit quickly here. The details are in the notes. So exactly as before we did with the traffic wave, we can derive some equations for the speed of the shock. So what we have is we have this equation that we wrote down at the start, that conservation of mass. So that's conservation of mass. That must equal 0, and that's true regardless. And when we derive the equations, we assume that the h and u are continuous, so we can. But if there's a discontinuity, then we can't take it inside it. But we can. So now we're going to so at s of t, there's a jump in h and u. Okay, this is the point. A shock. So what does that tell us? Okay, so we get d by dt of the integral from some constant to the position of the shock, and then some position of the shock, because remember it jumps at that point to x2, rho times h. And when we take the integral inside and we shrink it down, it's going to vanish. But we're left with, we've got to include the effect of this changing position. Right, so we've got to include the time derivative of that. Okay, we're going to shrink x1. We take the limit as x1 goes to x2. And likewise here, this is simply going to be equal to rho UH at, okay, S minus times S plus, okay, which is either side of the shock. So x plus is above the shock, just above it. S minus is just below. Alright, so no dramas here. So this is just going to be exactly what we had before. The rows cancel and we get h plus times d by dt of s minus h minus times the time derivative of s. So this is the value of h on the one side, this is the value of the h on the other. Minus u plus times h plus plus u minus times h minus equals 0. Okay, so that's one equation, and then the second one comes from the conservation of momentum, and that's a little bit trickier to write down. I'm just going to write it down here for you. I'm not going to derive it. Okay, it's derived in the notes, but I'm just going to write it down. So these are the equations of the shock, because the shock is two equations that govern it: h plus u plus ts minus h minus u minus dts equals u plus squared h plus u minus squared h minus plus a half g h plus squared minus a half g h minus squared. Okay, I'm not sure what you get out of seeing you write down those equations. They're in the notes anyway. But it's these two equations that you have to solve that give you the speed of the shock. So we're going to consider two simple cases that we're going to talk about. So let's just clear this. So conservation laws give us these laws for the speed of the shock, and we're going to have two because we have two equations. So the first thing we've got is a hydraulic jump. So what this is, it's a standard experiment and there's a movie on it, but you've got fluid, we're doing it the wrong way around. So normally it looks like that. So over here we've got U minus and H minus, and over here we've got U plus and H plus. And this, the U minus is greater than H plus. So we've got fluid coming out at a high velocity, and then suddenly it goes through this region here. It's turbulent. It's exactly what happens if you put a tap down onto a flat surface, onto your sink, and you get this pattern coming out, and it's easily to form in the lab. So it doesn't conserve energy, but it does conserve momentum. And this shock here, the speed S, is stationary. So there's some system here that it flows up here too. There's something that keeps it in equilibrium to balance, because the water will become deeper here and go slower, or become shallower if it moves this way. So ds dt is equal to 0. And then you end up having to solve a system of equations, right? So now you've got u plus, and that's just because this is the flow rates, right? They have to match. The flow matches what we talked about, and that makes perfect sense. It's conservation of mass. So we've got u plus h plus going this way, and u minus h minus going that way. Okay, and then the other equation is u plus squared h plus a half g to h plus squared minus h minus squared equals 0. Okay, and you can solve those equations, and there's a discussion in the notes here about how to solve it, and you end up getting an expression in terms of this Froude number. Okay, but you can imagine how you could solve these, whatever method you wanted to use to solve these equations, you could work out what u plus and h plus are. Given you have to know two of them, you've got to know u minus and h minus. So maybe that's the only thing that's important, right? So these are known because they come from the flow. Okay, so you can imagine how you can go and solve that. And the other, there's quite a good movie on the notes that shows you about a hydraulic jump and experiment, and explains to you how to derive the equations and everything. It's quite good on that. Okay, it's a standard sort of physics problem, engineering problem. And the other one is the shallow water bore. And this is something you commonly see at the beach, but you've got a mass of water. So just remember, when you get at the shop, then there's a turbulent zone at the shop. So here, this is still water. And you're interested in what? So the shock is moving here. But what you've got here is that you've got H plus here, but U minus is equal to 0. And here we've got U plus is equal to V, some velocity. And this is H minus. Okay, I think for some reason in the notes I've called this H0 and H1. Okay, so again you get the system of equations, the conservation system of equations. You can write down those system of equations and solve it. I'm just going to show you here quickly on the... Okay, I'm going through this quicker. I'm kind of reached exhaustion with recording these. So there's a system of equations here for you to solve. And there's an example in the assignment. I asked you to try and solve one of these system of equations and find out about it. And there's this wonderful thing here of this, the 7 bore, okay, which is basically a wave that comes up the river, and the rise in the fluid is so rapid that it travels up as one of these hydraulic jumps. It is equivalent to it's a moving hydraulic jump, moving into the still water. There's a flow of water coming up the river. So behind this surface here is a flow of water, and they catch it and ride it up. Okay. But this doesn't look too tricky a system of equations. I don't think it's got three. The unknowns in it are the ds dt, the speed that it's moving at. You know the height of water in the fluid here. You know the velocity here. Okay.